Hey, welcome back. I'm just pulling up our homework 3, looking at like how throwing distance varies for how far can our two made-up people, Pat and Jim, how far can they throw a baseball. And just double checking our stream setup. Sounds like we have sound, looks like we have video, and let's try running in there. So we had a nice discussion about like what are some variables that affect throwing. Like when you're throwing a baseball, it seemed like some of the things that we thought were important were strength, fatigue, form of the throw, and it seemed like maybe form might lead to some of the initial values that we have. So like arm length and body positioning, some of those are limited from person to person. Like your arm can only reach so high as you're throwing a baseball. But one of the things we came up with was like, all right, well maybe there's some kind of some kind of loss in how a baseball gets thrown. So I do a certain amount of work to get the baseball to throw. So now there's some losses in the work to throwing efficiency. So maybe that would be like our form of I did work and the actual 1/2 mv squared is some percent of that. So different people could have different throwing values for that. And then the other thing we thought of was fatigue, of like maybe we're actually reducing the amount of work done on the baseball, and so whether our form is good or not, like if we're able to maintain form as a function of throwing, it's another option. But I wanted to try to see if I could come up with a way of maybe implementing like some kind of sigmoid function on our throwing results, and just play around with like how to start taking an idea and quantify it into. So let's say that I do want to say that the number of that fatigue is based on the number of throws. So 1, 2, 3 throws, no difference, but maybe after 100 throws, now I should drop to like 50% of the work, or maybe like 75%. And one way I could talk about that would be, all right, so let's make sure we have everything kind of running. And so here, this t-test is telling me that, hey, it's not there. Continue. I kind of wanted to play around with this like explain error too. Oh, cool. All right. So it does suggest, that's pretty useful. So it tells you to add that line of code above it. So import it and then run it, and then we get a nice like t-stat. Tells us our degrees of freedom, our p-value. We can look at 1 point. So right now, based on different, so right now what we're assuming is that Pat and Jim both have different strengths. Like Pat has 3 joules of extra work that she can put into throwing a ball, versus Jim, who can only throw with a 35 joule. And let's close that out. But what if this was the same? Like what if we said on average they're about the same, but now I want to look at like what if there's fatigue? What if Pat and Jim have different levels of fatigue? Like maybe Pat is a professional softball, or like has been playing softball for a decade, and Jim is just sort of picking up a baseball and throwing it around. So maybe they do have similar strength, like 35 joules of strength to put into this ball, but maybe Pat can throw for longer, and maybe she doesn't like drop strength as much. So let's try ChatGPT. let's log in, jump in with Google. I need you to act as a Python. I need you to play the role of a Python programmer for scientific computing. I need a sigmoid function that starts at 1 and decreases to, let's say, 0.5 as the input increases from 0 to 100. So at 0, at the first 2-3 throws, we should be at 100%, and then by the time we get to 100, maybe it's like 50%. Make a Python function for that. All right, cool. This is kind of what I was expecting of, like, we have a 1 over an e to the negative 0.1, 50 minus x. So that is a sigmoid function, and it's one of many ways of talking about, like, a smooth transition curve. And let's see, we'll copy this and we're gonna put it in here to start. So we want to do a little bit of troubleshooting here. So we're starting at 1, and by the time we get to 100, it becomes 50%. And let's add our own inputs here and say, like, tired level equals 0.5, and we'll call this tired level, and this one's going to be tired level, and then tired rate equals 0.1. So what I'm doing here is I'm checking to see if I can change these inputs so that now I've got this input x, and really I want to call it like n. Oop. Like this, and like that. Call that a capital N so that it's, as I input the number of throws, default is that it goes from 1, decreases to 50%, and now if I change the tired rate from 0.1 to like 0.3, make it 3 times faster, now it becomes steeper where I don't get tired as quickly, but there's a quicker drop off. And right here, this is our 50% line. So it's saying that after 50 throws, that's like our halfway point. So let's maybe call it like our halfway point, like So now if I change the halfway point to 10, after 10 throws, I'll be at about 50% of my tiredness, versus after 70 throws, now I'm shifting that whole function over. So now I've got some control over how tired my tired level is. What is my tiring rate? Like, do I want it to be fast or slow? So put it back to like 0.1. So here's kind of like a slow decrease. We can call it 0.2 if we want it like a faster decrease. And now if I say that I can always throw at 35 joules or 38 joules, then it's going to be 38, and then at the end of my session of trying to throw 100 baseballs, now I'm down to 50% of that. And let's see what this actually looks like when we're plugging this into this thing. So if I say that this is all going to be one session, so here let's change number of throws to 100, so we're going to compare Pat and Jim. Now I'm saying there's no difference in their actual average result, but let's say Pat has a little more precision than Jim, just to see how things kind of change. And now, and then we'll keep the angles about the same. I mean, really, probably if we're saying that Pat has better form, then maybe we would want to say that form is related to that angle, but that's up to you. For now, I just want to process this Pat W of saying that how tired am I for all of this. And what I'm going to do is, here I've got this function that goes from like 0 to 100. And I'm just going to plug in, like basically take these values and multiply it by the number of throws here. So I'll take my, what did we call it? Decreasing sigmoid. It's kind of a boring name, huh? So let's call this like fatigue sigmoid. And you know what? Let's do this. We'll plug in two different values. And I already imported this matplotlib. I already imported, I imported this stuff, right? So all I need is that sigmoid. So Pat fatigue, better player, more not fatigue. What's the opposite of fatigue? More not fatigue. I'll think of it later. More not fatigue. Versus, and then we want to do this. Let's say like, call that gym fatigue, like that. And then Pat fatigue. And then this one's going to say gym fatigue. This one's going to say Pat fatigue. So right now I'm plotting the same thing, they're both the same, but let's say that Jim's tired level is, well, let's say that they both decrease to half. But let's say that Jim does it faster. So right now, let's give Jim like a 30 halfway point. So at that point, he's at the 50% mark. And then we'll say that he gets tired faster than Pat, kind of like this. This might be a little extreme, that maybe Pat can throw 100 throws and still not be at 50%. So maybe we'll call this like 60, so that Pat is slowing down. Pat's getting less strong, slower than Jim. So Jim hasn't been training, has the same strength, but has a bigger drop off. And here, whether or not this is true, this is something that we could probably measure and figure out, and we could probably back calculate it based on throwing results or something, but increasing fatigue function for Pat and Jim. And now the next part is just taking here. This one has 100 values. That's annoying. All right, we'll just do this. Take this, paste it in here, and then take this one, paste it in here. And instead of X values, this is going to be an A range from 0 to N throws. And instead of X values here, this one's going to be np.arange of 0 to N throws. And I took the same inputs that I had from above, and now the only thing that I'm going to do is rewrite Pat W and Jim W as Pat fatigue times Pat W. Oh wait, how do I get that? That's what I want. Times, yeah, like that. That's kind of nice. So it already knew what I was trying to do. So I was trying to take this Pat work, and what I did to get it to actually do it is I hit tab. I was trying to hit enter, but it wasn't working. So tab will get you, if it's showing you, hey, are you trying to do this? You can hit tab and let it autocomplete. And just some notes. Update work with fatigue losses. Where it's a function of the number of throws. And let's see what happens to, I'm not going to change any of this stuff because I'm not adding like drag or anything. So let's just see what happens. Now we have 100 throws. So there's a whole bunch of stuff going on, a lot of different distances. And now we can see pretty clearly that there's a very small p-value here. So it seems like the two means are statistically significantly different. And now we're seeing like very, very different histograms of results because we're not looking at something where it's uniformly variable. We have this like function of, kind of like a function of time, where every throw is changing the average value. So now we kind of have like two different places of like, here's the average when we're fatigued versus average when we're not fatigued. So here's Jim doing his best in the first few throws and then throwing a whole bunch of shorter ones. Or sorry, doing his best for a little bit, but then quickly fatiguing and throwing a lot of lower throws. And here it might not even make sense to use a t-test, because a t-test is assuming that we have a normal distribution. And now we're kind of ending up with like a binomial sort of distribution. Like things are changing in this case. We can add some bins. We can increase number of bins. Here, let's do that. 20 and 20, just to, and we should put a comma after that, 20. And that's just gonna uniformly decrease the bin sizes. So Pat, we can see, was throwing further for longer, even though they both started with the same average throwing. And we would probably notice a big difference even if these distributions were the same. Yeah, so even still, Jim starts throwing shorter, quicker than Pat. So Pat has what looks here, it's almost a uniform distribution, right? Like if I squint and say something else is happening. So that's kind of cool. And let's go Pat X -1. I wonder if I could do this just to see. Oh no, I want code. What I want to see is a plot of number of throws. So I'm going to plot like 0 through the number of throws and just looking at how it changed as a function of throw number 1 versus throw number 100. And here we can kind of see that same curve that we just plotted up above, right? Where at first both players are throwing the ball the same distance. Like there's probably no statistic, there should not be a statistically significant difference between all these throws for blue and red. But then over time we see that Jim is dropping off pretty quickly. Meanwhile, Pat is kind of holding her own and throwing the ball a little further. So anyway, I wanted to share that, since this was one of the things that we identified in our discussion of like, hey, this would be an interesting thing to, this was one of the factors that we thought was like the most interesting and probably would have the biggest effect on how people throw a baseball. And I made a lot of assumptions here in that 50%. That 50% is probably really low for someone like that's fatigued. I mean, that seems more like at throw number 500, maybe you're doing like half power. So then you would end up, it's not quite, well, it almost ends up at half distance. So for the most part, work and distance gone. And roughly we can think of that as like work is force times distance. So if we have half the work, we have half the distance. It's not quite that simple because we have like a projectile motion problem, and really we're like doing the work to create kinetic energy, but all things considered equal, half work, half distance. And that's probably a bold assumption to make. Maybe really we should have said something like instead of 50%, we could say that this tired level is 0.85, right? And just compare so now, oh, why did I end up down there? I messed something up, my tire, because now I'm starting at 170%. I'm giving it my all, Red Bull style. Give it 150%. I broke something. Tired level plus tired level divided by that. I thought that was so here. Oh, I think because it was 50, maybe this should be 1 minus tired level. Like that. So that one shouldn't change at all. And now if I change this to 0.8 and 0.8, we go from 1 to 0.8. All right, that was the issue there. So what I did here was, because I'm trying to change this sigmoid to go from 1 to 1/2, or in this case 1 to 0.8, really I want this thing to be multiplied by 0.2. Like I want the magnitude of my sigmoid function to be 0.2, and I want it to be 1, so I have to add it to the tired level. So 1, so tired level, and 1 minus tired level. And we could probably play around with ChatGPT to do this for us. But yeah, and it gives us some of the inputs there. But that's okay. We figured it out without you, ChatGPT. So let's see what happens if we do this. Oh, wait, let's copy that one in and paste it in here. Like that. And what we're seeing here is p-value went up because I'm saying both of them are getting tired. They're both going from 100% to 80%, so they're only dropping by 20% sort of work that they can put into their baseball at this point. And now we're starting to like clump those two distributions back together. That's kind of what I'm seeing here. Let's see this. Yeah, now I can still see like a downward trend, but there's a lot more noise in it because I'm going from that first kind of 50 joule, or whatever, that 38 joules, which is 50 meters, down to that 80% of that. Cool. Yeah, and now if I squint, maybe I could make the case that this is all random. But now the cool thing is kind of like if I increase number of throws, like if I change this to 1,000, like I force the two players to do 1,000, most of that, it's going to be swamped by my 80% performance. So all this stuff, I'm going to have over 800 throws, over 900 throws where they're exhausted. I do that, we'll definitely see, yeah, now there's like a tiny peak over here at their max, but then both of them are basically throwing the same distance because they're both exhausted. And we also see that here is that they were doing great, and then for the next 900 throws, not so well. Anyway, that's just, I wanted to go through that as talking about how we can actually implement this stuff and give a sense of how to use the tools that we have so far. And I know we talked about like a warm-up phase, like maybe at first you're 90% and then you go up to 100. In my case, what I'm assuming is that they already warmed up and now they're ready. They're at 100% because their arm's loose and kind of warmed up. So if I was going to talk about this, one, if I'm introducing a function of time, I definitely want to show new plots of saying like, here is my new function of time. This one's kind of lame, right? Show the actual function time. So here is my, where x is, this is not x, this is number of throws. So number of throws, and fatigue is going from, I guess really I should say like performance, because this is really like 1 minus fatigue. If you have 100% fatigue, then anyway, it's a number, like 1 minus that or something. But so in this case, we could add like a text down here in the figure above for the fatigue function. Pat and Jim's fatigue ranges from 100% performance at throw 1 to 80% performance by throw number 100. The loss in distance is calculated as W equals fatigue and what do we want to say here? W times W. There we go. Times W. And I'll just copy this from above. So as the player, the fatigue function is a sigmoid that has two further parameters that change for Pat, Pat and Jim. And here I could grab the actual should I copy that? Let's see if I can paste this in there. delete all this, and I just want how does that look? And k minus x0. What's that one? The halfway point. So I'm going to call it n1/2. And delete that. Where Pat has k equals, what did we put for Pat? K equals 0.1. And n sub 1/2 equals 60. Wow, Jim has and maybe this would make sense as a table instead. I think I said 0.2 and 30. And this should say, this is like number of throws, right? And then kind of, this is like a fatigue per throw. Or joules per throw, maybe a joules per throw or something. I don't know, but it's unitless here. Higher K values equate to steeper fatigue curves and higher n sub 1/2 values equate to longer longer performance, something like that. Longer performance, e.g. at n equals n1/2, fatigue equals 50%. And I think I have to do that. And all of this is just describing like how I'm like actually implementing this idea that fatigue is a factor in throwing a baseball. Like I'm just trying to say, okay, I have this new curve, I'm gonna go from 1 to 80%. So both of them are doing the same 1 to 80, but I am changing two factors. One is making the slope slower for Pat, and the 50% mark. Oh, whoops. So I said 50%, but really it's 50% of the equals 90%. Halfway to fatigued. So I'm glad I was reviewing that. Halfway between 100 and 80. That's what my n1/2 is showing. So Pat decreases slower and hits the 50% further on. Jim increases faster and hits that 50% faster. And those are kind of the two ways that I can vary that function. And then I can jump into my analysis of like, is there a statistically significant difference between these two averages? And for the most part, like, yes, Pat is throwing 1/2 meter further than Jim. Am I still doing 1,000 throws? Let's go back to 100 throws. So 3.4 meters farther than Jim after 100 throws. And here I can talk about how those two functions, there is a difference. The blue curve for Pat is different than this red, kind of squinting the red curve for Jim. But all right, cool. Thanks for joining. Hope this helps as you're thinking about like implementing and kind of quantifying like what is different when you're considering an analysis. And the power of like doing things in a Monte Carlo method like this is like you get to just play around, like see if you increase this, like how does that change what you would actually measure? And then can you actually measure it? Like if I saw a difference in 3.4 meters from one person to the next, so 10 feet, I mean, maybe that is, rather than having them like continue throwing 100 more balls and see if there's a difference. Like maybe there is something else going on. So maybe you could start tracking like number or distance per time thrown, like how many throws versus distance. All right, cool. So again, thanks for joining and hope this helps.